direction of the electric field. So the force on the negative charge is in that direction. So it will rotate about the center. We assume that there's a tight enough bond that they will not split apart, that the distance between them stays the same. We're not ripping this in half, we're just rotating it. So this would be R positive cross F positive plus R negative cross F negative. Now cross products. I need to have some angle in here. And so I'm going to establish that angle there as theta. When I'm doing cross products as opposed to dot products, what's the meaning of a cross product?
You get a vector.
Say it again.
You get a vector.
That is true. So if I have vector A and vector B, some angle between them of theta, let's just start out with, what's the magnitude of the cross product?
A plus, or A times B cosine theta.
Sine.
Sine theta, yeah. Why sine? Cosine dot products.
Perpendicular.
Yeah. Cross product cares about perpendicular. If you think that of the cross as two small little perpendicular line segments, that's sort of potentially a memory trick for cross products care about perpendicular. So the perpendicular component of A would be A sine of theta, so this is going to be AB sine of theta. Now test those memories. What is the direction of this cross product, A cross B? Pardon?
No direction.
Oh, no, there is.
Into the board.
It is indeed into the board or page. Put your hand in the direction of the first vector, and then you want your fingers to curl towards the second vector. Thumb points in the direction of the cross product. So into the board, and so A cross B, in this particular case, magnitude of AB sine theta, and the direction would be, given our convention right here, into the board. So this theta, though, is the angle between the two vectors. So let's take a look at this positive here. My R positive vector is going in that direction, from the pivot point to where the positive charge is. There's my R positive right there. My force is going to the right, because again, positive charges are being forced in the direction of the electric field. So there's my force. So the angle between them is theta. Let's go ahead and set up a convention here. I'm just going to go for the old boring IJK like that. So I to the right, J up, K coming out. Right-handed coordinate system, because I cross J is K in a right-handed coordinate system. So this is going to be L over 2 times the force on the charge, which is just Q times the electric field. And R cross F would be into the board. So negative K hat. Plus. So we have R negative going this way. Force negative going to the left. Again, that angle is theta. So we're talking R negative going that way, force going this way. Not drawn particularly well, but those are congruent angles there. So R is going down that way, F is going this way, so R across F puts us into the board again. That's a good thing, because the magnitude will be the same. If it was the opposite direction, we'd end up with 0. So this is L over 2 Oh. What did I leave off? There's a mistake there.
Unit. Unit.
Sorry, missed it?
Unit.
No, not a unit issue.
The sign. Is it the angle?
Yeah. Sine of theta. Plus L over 2 Q times the electric field. Sine of theta, negative K hat.
Would it be negative L over 2, because the R is going in the opposite direction for,
The two ways of dealing with direction, with especially in the second semester course, is to think through the direction and then sort of put it on there. That's what I did here. I know that the direction of the torque is going to be into the board, and so I accounted for the negative sign at that point.
okay.
We could have done it differently, in which case we would have had a negative here, just an alternate way of doing that. Our negative hat's going down like that, so that would be L over 2, negative L over 2 cosine of theta I hat minus L over 2 sine theta j hat cross the force, which is negative Q E j hat, and actually that vector symbol should not be there. And so ultimately we'd have a negative here, which is positive, and then I cross j is k, and somehow I'm off by a sign somewhere. Where did I screw up? Oh. The charge is negative Q. Wait a second. No, I thought through the sign. I know that the force is in that direction. It's in the negative. Oh. Good thing I'm not operating heavy machinery today. So that would be, the magnitude is Q times the magnitude of the electric field. The direction is that way, which is negative I hat, not J hat, as once claimed. And so the I hat cross I hat is 0, that doesn't count. So J hat cross I hat is negative K, and then the two negative signs would cancel out. So I'm left with just a single negative sign. So L over 2 QE sine theta negative K hat. That's what I have there. And so now what I'm left with is QL, magnitude of the electric field, sine theta negative K hat.
QL, the electric potential.
Sorry?
Is QL equal to the electric potential?
Wrong word. What is it?
Dipole moment.
Yeah. So that's the magnitude of the dipole moment right there. So of course we can bring that into it. Because why on earth would you put it in terms of letters that you've been using already and instead of brand new letters? So I have negative P E sine theta K hat. But recognize here, this P E sine theta is just the magnitude of the cross product between P and E. So that's P cross E. The question is Do I have to throw a negative sign in there in order to account for the direction? Well, let's think about that. If I have P going in this direction, and I have E going in that direction, what is the direction of P cross E?
Into the blue.
Indeed. So, I don't need to add an extra minus sign here because that negative K direction automatically comes out of that. So, the formula for torque of a dipole in an electric field. All right, questions to hear? All right, so let's take another break, just a 5-minute break. Come back, and we're gonna do 2 more problems from this chapter. Then we're gonna put a nail in the coffin, talk about quizzes and neat stuff like that. So just to pump you up, bring you down, to calm you down, let's take a break, pump you back up. We're gonna finish up chapter 24 and talk about assessments.
So this is chapter 24?
Yes, chapter 24. Everything we've pretty much done today has been 24, except for the stuff that we pulled from 23 in order to supplement 24. And then after that, we'll talk about a simpler way of finding the electric field from an infinite plane and so on and so on. There are other ways of doing the exact same stuff that we've already done. And again, I'm gonna let the recorder just go so that I don't have to remember to turn it back on.
It was 104 degrees.
104?
Yeah.
Ah, okay, thank you. Sorry if I put you on the spot there with what are you planning to do?
Oh no. Yeah. It's yeah.
But at least I have recorded the shame that I have in my daughter. So if she ever sees this. And her husband is biochemist. Did I teach her nothing? think we're all back. Okay. All right, so we're sort of bringing some stuff together here. Get away from the pesky dipoles for a moment. We have a curved line of charge, quarter circle. Oh, I need to give a radius here. Radius 50 centimeters. What is the electric field at point P? All right, so before we actually do any math here, what do you know about the final answer for the electric field at point P?
The units,
Okay, what would the units be?
newtons over coulombs.
Presumably.
Be away from it, from the quarter circle.
All right, going in, can we pin down, you said away from it, so just somewhere in the fourth quadrant, or can we be more specific?
Down towards the fourth quadrant, down to the right. Yeah,
Wait, at that 45-degree angle? Or not that specific?
not that specific, no. Just in that general direction.
All right, so we'll be in the fourth quadrant. Can we pin down the angle?
Yes.
Can we pin down the angle?
Yes.
Yes.
All right, what is that angle?
45 degrees.
Yes, absolutely. Symmetry. If we look at this right here, and couldn't tell from my drawing, there's no reason why it should be more dominant down or to the right. It has to be because of, it's just as likely it's being pushed down as much as it's being pushed to the right, it would be a 45-degree angle. In other words, we only have to solve half the problem, and we know and we can figure out the whole thing. So, we have a distribution of charge. We've drawn the picture. We established our dq here, so I have some charge here, dq. I know the direction of the electric field from dq will be in that direction right there. Ultimately, I know the answer is going to be at a 45-degree angle, but for right now, we have to keep it generic. And I have to make up a unit, or make up a variable that will eventually go away. So I'm just going to call that one theta there. Because why not? Since I only have to solve half the problem in order to get the full answer, because again, it's a 45-degree angle, so the magnitude to the right and the magnitude down will end up being the same. That's theta, that angle's theta there, which means that I'm gonna look for I'm basically gonna integrate either the horizontal piece or the vertical piece. It doesn't matter which one, pick one. You wanna solve for the horizontal piece or the vertical piece?
For the horizontal.
All right, so we're gonna solve for that piece, the part in that direction right there, which would be the sine. So the differential of my electric field is going to be equal to K dq over r squared. That's the magnitude. Now we have to take the direction into account. Sine of theta. I'm gonna make up positive. So I hat, j hat. And so that's the I hat piece. I guess I put a little subscript I there just to, I hat, just to indicate, we're only looking at part of the electric field here, that's not the total electric field. As before, we have three variables here, well, potentially three variables. Actually, we have two variables, because R is constant, because it is part of a quarter circle. So this is gonna be K over R squared. Integral, put the I hat out front, dq sine theta. We have to get it in terms of a single variable. All right, so we have dq here. We have a uniform linear charge density. So dq is going to be equal to lambda d, and use the letter S here. I'm not using L because traditionally L is a length in some particular direction, and we are dealing with a length here, but because this is part of a circle here, it's an arc length, and S for arc length. From the Latin, or studia. Now that doesn't get it into a single variable quite yet, but I have K I hat over R squared, integral of lambda ds sine theta. Still have two variables, but I do have a relationship between S and theta. If I have a circle here with some arc length S and some radius R, some angle theta, what is the relationship between SR and theta?
S is equal to R times theta.
Yep. And so ds is equal to R d theta. If we think about the angle theta being from the vertical to where this infinitesimally small bit is, then if I just draw my two segments here back towards the center, this is an infinitesimally small change in the angle, so this is d theta, and that is so badly drawn, but we're gonna go with it, because I could try again and do even worse. And so now, I plug in R d theta into here, and so I have K lambda I hat R over R squared, integral of d theta sine theta. So this bit right here, this R d theta is ds. And again, R is constant because it's a part of a circle. And so I can now establish limits of integration because I have a single variable. What are the limits of integration for theta? Yeah, to pi, 0 to pi over 2, so 90 degrees. So 0 to pi over 2. And why pi over 2 and not 90 degrees?
It's a maximum. You can go basically, if you go past that, then I'm not sure what that.
No, I mean, why do we want to express the limit of integration in radians and not degrees?
Because
Is it
when,
a liquid?
There's another reason for it.
because when we, like S equals R theta was in radians.
Yeah, that does assume radians there. And so now, the integral of sine theta is
Constant.
negative cosine. So I have K lambda I hat over R, because that R cancels out with one of those, times negative cosine of theta from 0 to pi over 2. So I have k lambda I hat over R times negative 1 minus 1. So we get 2k lambda over R I hat. And again, don't forget, we've done the bulk of the problem here. However, that's only half the solution. We've already thought through the full solution. So the full solution is 2k lambda over R I hat minus 2k lambda over R j hat. This was I know I've done this on the test before. I think I gave various shapes and I said, pick one, find the electric field for it. And the electric potential for the same.
Isn't cosine pi over 2 0?
Oh, it is. So you want me to do it correctly? Is that what you're going for? Thank you. Any other problems?
What did you just ask? I didn't hear.
Oh, what you said?
I didn't see what you changed.
When you plug in the pi over 2, cosine of pi over 2 is 0 and not -1. That should have been a 0. Was that the part that you missed? Of the correction?
I missed, like, I couldn't see because of traffic, I guess, but, like, what else did you change?
Oh, because that's a 0, this whole term here becomes 1 instead of 2. So I erased the 2 from this piece right here, and then I erased the 2's right here.
Okay.
So what was the explanation for why it was minus the j hat?
All right, because I know, because of symmetry, the magnitude in the horizontal direction is the same magnitude in the vertical direction. Because there's no dominance here.
Because of the 45 degrees, right?
Yeah, so because that's 45 degrees. And the reason why it's negative is because since it's going into the 4th quadrant, and I said right here, to the right and up is positive, since it's going down, that's why the negative's there. If we solve the j hat piece of it, the difference is that instead of sine theta, we'd have a cosine theta. When we integrated, we'd have a positive sine theta here, which would then put in, no, it'd actually be a 1 minus 0. There's a, oh, no, we would have put a minus sign up front if we were doing the j component, because we knew it was down. Sorry. Less dynamic than I originally was thinking when I started that last explanation. Was your question answered?
Yeah.
Okay. Any other questions? All right, now an application. Let's see, what do I want to make the particle? I'm gonna shoot a proton. I have two parallel plates. This is negatively charged and positively charged. We assume the plates are close enough that the electric field lines are indeed just perpendicular to the plates and parallel to each other. I'm not worried about the subtleties at the edges where it might bend out some. The proton's going to enter into this electric field. And as it enters, it's going to start to curve and shoot out the other end. And what I want to know is, what is that angle? I do need to give some numbers here that this length, this direction is L. And do I want to put just some electric field E. And I said proton there, we can make it a generic charge of Q. We'll solve it for Q, we can stick in the proton later, we'll just keep it generic for now. And it has some initial speed of V sub naught. In the horizontal direction. So my initial velocity is V sub naught, and sure, what the heck, I hat, J hat. It's a two-dimensional problem, we can't get away with just plus and minus, we do have to put some unit vectors in there, I hat. We are assuming that the electric field is controlled by somebody in a control station who can adjust it a little bit, so if he needs to adjust the direction that the charge is being sent afterwards, he can. This is in high energy physics. You basically play around with two things in order to get particles to go shooting in a particular direction. You can either play around with the electric field or the magnetic field, which we'll get to later. And so if you adjust the voltage between these two plates, you can adjust the amount of charge that's on them and the electric field between them.